Well, thank you, Dr. Menon, and it's great to be here. Even though I'm always in the research atmosphere, I always like to go sometime out into the completely different environment, such as like this, and get a chance talk with students, faculty. I've been actually doing that quite a lot now this day. I mean, the end of this month, there is another nanoscience lecture series at Octon Community College. They are organizing. It's a NSF, funded program. So I'll be there also talking about the nanotechnology and some of the kits that we have developed for teaching students about nanotechnology. But it's great to be here, and I was really impressed with the labs that Dr. Menon showed me. And I think this is very important. I mean, the Argonne National Lab is a great resource just down here 7 miles. So and she is coming there working, and that's how this connection is made. So I think you guys should really take advantage of such a great resources available right to your there are many students which are not that fortunate to have this kind of great resources available right here in Illinois. I mean, we have 2 national labs. Fermi National Lab is another great resource. So I will urge you, I mean, there are so many different programs at national labs, summer programs, and now Dr. Menon is our point of contact. So, I mean, she can tell you, even more about what the things, goes there. But let me, start with the presentation today that I, put together. Some of the things there, I mean, I structured my talk mostly about some introduction about the nanotechnology and the research work that I do. But I actually filtered down that research work in such a way that hopefully you will get to understand. For example, I'm a material scientist, and I work with the different allotropes of carbon that Dr. Menon mentioned, including diamond. I mean, diamond everybody knows, but what are its technological importance? What are the scientific areas where diamond is useful for us? What's the next generation of technology that we are working with diamond? So that's some of the things that I will touch upon. And there is a new material, graphene. If you know graphite, and if you just peel off the one atom layer of a graphite, it's called graphene. And in 2010, the 2 scientists from UK got the Nobel Prize in physics for that. So it's completely changing the world right now. And I'll touch upon what are the things that we are doing in graphene. And then I'll talk about some introduction about the nanotechnology kit that we have developed that could be utilized for teaching students about the nanotechnology. So there are some of the things that I may not be able to cover because of the time, but I think you're welcome to ask me any questions later on during the talk. So let me just give you a brief introduction about the Argonne National Lab. So it's a big lab, about 3,300 employee, and about 1,623 are the PhDs working there, and our annual operating budget is about $800 million. And the kind of things that we do here at Argonne National Lab is really the next generation of things. I mean, what we are working on today, maybe 10 years from now, these things will be in the market as a product. So I think it would be great, for you to learn, what are the things that we are working currently right now in this area. So I work in the Center for Nanoscale Materials. That's one of the division at Argonne National Lab. There are many different aspects, of science that we looked at, whether it is biology, whether it is, physics, and nanoscience or advanced photon source, where there is a combination of many different aspects of science that we look at. But Center for Nanoscale Materials is established by Department of Energy in almost 2006, and there are 5 such centers at 5 different national labs. And the main idea of having these centers is that this will be the centers of excellence, which means we'll have all the state-of-the-art facilities available that general university won't have that kind of facilities. So the idea is that you write a proposal to us, and if it meets our criteria, then you get a time to come and use those facilities for free completely. And it's not necessarily just from the US. Anyone from all over the world can access this facility. So this is a great resources for researchers, students, industry to explore new frontiers in science. So, I will talk a little bit about nanotechnology, and there has been a lot of discussion, and you might have seen also in some of the magazines, and we have been talking about nanotechnology for many years. So what exactly it's having impact on our lives? Sometimes there is more even hype than what exactly it's happening. So that's why I put together some list here, which is actually changing our lives in many different ways. The nanotechnology, advanced materials breakthrough technology in medicine, energy, water filter, water purification. So these are just one examples. Also, there are many advances going on in energy storage in terms of battery, transmission, and also conversion of many forms of different energy into different resources that could be utilized. The most important thing, of course, is the computation. Everything is now based on the machine learning, and you might have seen many examples of that around you, including the Facebook now is on the top right now. There are certain disadvantage of that, but many things in the science could be put to use about the data generation that could be utilized for predicting things well in advance. Weather forecasting is also another area. There is a lot of research going in the area of healthcare, and in atomic precision, looking at the surfaces that we were never imagined that we'll be able to. We can look at even inside the atom now, and to look at how the spins of the atoms could be used for what is called as the quantum computing. So there are many different things going on in the nanoscience. So let me just give you, when we talk about nanotechnology, what is important is the length scale. So when we say nano, how small is the nano? And I think you can get to know just by looking at this beautiful picture. This is a family vacationing on a beautiful beachfront, and if you just look at the size scale analysis, the sun, the diameter of the sun is almost 10 to the 9th meter, very large object. And if you look at the other objects, which is the length, height of a person, about 2 meters, and then since they are on the beach, in the sunny beach, if they are applying some kind of sunscreen lotion, which consists of nanoparticles of titanium dioxide, and their particle size is 100 nanometers, so another in the length scale. And then if you look at the water molecule, the distance in the water molecule is about 0.275 nanometers. So you can get the idea of, when we say nano, how small it is as compared to the big objects, like comparing with the sun. So when you make this thing small, many things changes, and as you go down in size, the properties of the material changes drastically. So how do you make nano? So there are two ways to make nano. One is a top-down approach. So in this case, you start with the material, and then you carve the material down to nano size using different tools that are available there. The other area, and this is kind of a micro machines, the size is in micron here. And then another area is called bottom up. That means you build from the scratch. You deposit materials. And so these are the two different ways of making nano, either top down or bottom up. I'll be mostly talking about a top down approach here today. And in here, this is an example of some of the nanowires which are grown by using the chemical vapor deposition process. This is bottom up. So in my group at CNM, I work on many different areas. And some of the areas, either making these micro machines out of diamond, which could be used, one day going inside the human artery, doing the kind of surgery which is needed. Why diamond? Because diamond is biocompatible. Its body recognizes that as a friendly. So you can actually produce these nanobots that go inside into the tumor operation, and then go through your urinary tract. So that's a very safest way, that we are looking at how these micro machines can be made out of nanodiamonds. There are sensors that we are building which is made out of, a nanowire. So this is a nanocrystalline diamond. I will mention, later on what's the diamond, what is nanocrystalline diamond, which has very high surface to volume, ratio. So any molecules, that land onto the surface, the electrical resistance changes of that nanowire drastically. And there is a selectivity that you can tag particular molecules, and so they will, recognize whether it is anthrax molecule or, whether it is something, completely different. So, and that's the very sensitive biosensor, that we are making, or any other sensor for that matter. We are also working on, utilizing this diamond as a piezoresistive. So, I mean, I won't go into too much, into the details. So piezoresistive just is that when you press something, it changes the resistance. So it's called piezoresistance. So when you dope diamond with the boron, then it has this kind of properties. So it's a very, very good touch sensor in that sense. So we are developing sensor which will be integrated, with the robots, so that the robots will know how much force that they have to apply to, pick up the delicate object like egg, or throwing a ball, a football or something. So these are the kind of things that we can teach them, but the sensor has to be accurate in that way to understand, what kind of forces that is needed. And then later I will talk about some of the things in lubrication. It's a very different area, and the oil is used everywhere for lubrication, but we are developing a next generation of lubrication based on graphene, which is completely solid lubrication. So you can imagine one day, I mean, everybody has a car, and then you have to change the oil in your car after some time. But how about, you never had to change the oil in your car, you just put a graphene and it will work forever. So that kind of thing that we are working on. And then I'll just touch upon a little bit about the next gen STEM kit that we have developed for classroom-based, approach where you can fabricate these nanowires, in your benchtop experiment without going into the, sophisticated lab like Argonne National labs. So let me talk about, diamond a little bit. And, diamond and graphite, again, these are the same, different allotrope of the same element carbon, but because the atomic arrangement is so different, one is extremely hard, whereas one, is a soft. And if you look at converting, diamond into graphene or graphite, it's easy. You just burn diamond, in air, and it will, turn into the coal. But if you want to convert the graphite into diamond, it has to climb this energy barrier, which is very, very high. And so generally, how the diamonds are created inside the earth crust, millions of years, they embed there inside because of very high pressure, very high temperature, and with the lava they come out, and that's how you excavate diamond. But you might be knowing this phrase, diamonds are forever, but scientifically speaking, diamond is a metastable phase of carbon. So graphite is the stable phase of carbon. So if you put diamond, in the air with the UV light coming, from the sun, it will take million years to convert the top layer of the diamond into some graphitic layers. So that's why, it's called diamonds are forever. But scientifically speaking, it's, every time it's degrading actually with time, but the degradation time is over a million years. So that's why, relatively speaking, we say diamonds are forever. So let me go to the phase diagram. So don't get scared with this phase diagram because it's very simple, and I'll tell you, how this works. So you have pressure and the temperature scale, and there are different ways of forming diamond. Okay, so generally, if you use the general method, which is called high pressure, high temperature method, which is started by General Electric, 1950. They actually built a tetrahedral press where they put graphite, squeezed to very high pressure and high temperature, and then they convert. So they exactly reproduce the same condition that exists, inside the earth mantle, and they convert the graphite into diamond. So that falls, in this area. It's called high pressure, high temperature synthesis. Then there is also another way, it's called shock wave synthesis. It's a very funny way of making diamond. You actually take graphite, you wrap up with the TNT explosives, put it in a big chamber, explode. And then because of the shock wave and the temperature, it converts the graphite into nanodiamond. And that's happens within this temperature and pressure range. But there is another interesting region here, which the temperature range is between 400 to 1000 degrees Celsius, and the pressure is actually less than atmospheric pressure. And that's called chemical vapor deposition, and that's what Dr. Menon is actually working on at Argonne, utilizing the system there. So you just use methane as a gas, and hydrogen and argon, and then you apply the activation energy, which could be either hot filament or microplasma. So you dissociate methane into the carbon radicals, and then that's how you synthesize diamond as a thin film. And it has a tremendous applications in that way. So that was the major breakthrough that happened, that allow this diamond film to form at much lower pressure and temperature. And that's how now we are utilizing it, or thinking of utilizing it for various applications. So let me go right back in the synthesis by using HPHT method. This is the team of the GE scientists, and this is the tetrahedral press that I mentioned. And in this you can form a diamond with a different color. Now it's very interesting that if you introduce the nitrogen as an impurity, it has a yellow color. If you introduce boron as an impurity, you have a nice blue color. This is, by the way, Hope diamond. If you go to the Washington, D.C., go to the Smithsonian Institute, and there you will see this Hope diamond already there. Very beautiful. But the level of impurity is just parts per billion, just one atom in billion atom. If it is of boron or nitrogen, then you change the optical properties. That's really amazing, such a small impurity. So, there are, as I said, the pressure is very high and the temperature is very high in this case. So, its use was mostly for jewelry purpose, not for technological purpose. But the way that we started working on the gas phase synthesis, and I think, in 1962, there was a first patent filed by Union Carbide on synthesizing diamond from the gas phase. And then in 1972, there was a major breakthrough by Russian scientists by using gas activation. They actually introduced the hydrogen gas, and that was the major breakthrough, because then you were able to increase the yield of producing diamond. And then all over the world, there was a lot of activity going on producing diamond films. So at Argonne National Labs in 1992, Professor Dr. Dieter Gruen and his colleagues were actually looking at this. And 1998, where I joined the Argonne National Lab as a postdoctoral, we actually worked on producing this diamond, and since then, there is a lot of research activity going on in this area. So, over the years at Argonne National Lab, we developed many different technologies based on diamond. And there is also a company from last 12 years now called Advanced Diamond Technology down in the Romeoville, which are producing different products based on diamond. So this is one example. This is a pump seal, which is made out of a coating which is wear and friction resistant diamond film. This is used in many chemical industry as a pump seal. And then there is also another product that is by Second Sight. This is the artificial retina, which is completely made out of diamond. And then we actually came up with the MEMS, micro electromechanical systems. This is used in advanced radar communications for defense industry. And then here is one application where these are the micro drill bits. These drill bits are used for intricate machining of very hard metal alloys. So this is a company, N-UNCD Technology in Wisconsin, commercializing these applications. And there are various others, but I'll just talk about now different things that we are doing. So this is the machine that we have at Center for Nanoscale Materials, and this is basically a big microwave oven. it's just the energy is very high, the size is very high, but it's the same concept of your microwave oven in kitchen. And what we do here is we actually synthesize diamond film by introducing different gases like methane, hydrogen, argon, and then raising the temperature of the substrate that you're going to deposit by about 800 degrees Celsius, and you get a nice, beautiful film of diamond on a silicon wafer like this. So if you look at the scanning electron microscope image, you will see the nice faceted diamond. But by playing with the different gas composition, you can either have a nanocrystalline or ultrananocrystalline diamond. Now, there are different usage of, changing the grain size and everything that I won't go into the detail. But with this, we developed the technology where, we can make a CMOS compatible. CMOS is the term which is generally used in semiconductor electronics for interfacing, the silicon technology with the outside world. And so this was the project that I mentioned, the RF MEMS switches that we actually worked on in making on large area, which is now on the way for the commercialization. So what are the applications of this diamond? So it's chemically inert, very high hardness. It has a very, very low friction. And then it is also, diamond is considered as a insulator, but if you dope with either boron or nitrogen or phosphorus, you can have electrical conductivity just like metal, so which is very useful along with its its chemical inert properties. It's also biocompatible. Some of the things that I won't go, it's a field emission property, means ability to emit electrons, and which is very good for various other applications. So these are some of the products I already mentioned. Some of those before, which are in the market by Advanced Diamond Technology, which is a spin-off company from Argonne. This is a water filter, which is used by using boron doped diamond, which produces huge amount of ozone and purifies your water. Mechanical phase seals, and some of the nanotechnology applications like atomic force microscope tips. This is used for imaging some of the semiconductor electronic components, where if you just use silicon tips, they wear out very quickly, but you're using diamond tips, so it can last longer. And recently we came up with this nanotechnology education kit. There is a company called United Scientific Supplies, which actually marketing that, and I think it's good to know that Dr. Menon has now, so you have access to this nice kit. So now I'll explain a little bit about how that works. So let's start with some of the things that I already talked about in a little more detail. So diamond micro machines. So as I already mentioned, as you go from big size, like this is a car engine, to a micro machines like this, and even smaller scale. So the surface to volume ratio increases. So as you go to the smaller size, surface is everything, and the surface is a very, very difficult to deal with, because it has a stickiness, it has a lot of adhesion. So if you want to make any micro machines, which are down to nanoscale, it's you actually face with a lot of challenges to make it work. So this is the one example where the micro machines are made out of silicon. So these are the gears, and then some of the examples, if you try to spin that, it wears down very, very quickly, and then you will see this kind of failures. And that is because of the inherent material properties of that silicon. It has a very high oxidation, which gives the high adhesion and higher friction. So people are looking for new materials where they can fabricate this kind of micro machines, where it will last much longer, will not wear down, and which will be much more efficient. So we looked at different materials. Silicon carbide is another such material, but in terms of properties, the diamond stands out. Diamond has very high hardness, very high fracture strength, very low friction coefficient, and very long wear life. So that makes diamond as one of the candidate material. And then we actually developed this technology a few years back, and here is one of the simple micro machine that you can make out of diamond. So this is called Chevron type thermal actuator. So it's very, very easy to understand that these are the two bronze that you see, and then these are the electrically conducting diamond. So if you flow the current through this, they heat. So when the material heat, what happens? It expands. Okay, so it heats and it expands in this direction. So if you actually provide an electrical pulse that is actually heating it, then you will cause this kind of motion, the linear motion. So this is what we have used in diamond. So by using the microfabrication technology, we fabricated this machine here, and I'll show you by using actuation. So you can clearly see how this, as you can clearly see, there is a linear motion that is happening there, so which is in few microns. So you can think of attaching that into the gear assembly, and then you can have any kind of motion. And then we looked at the amount of power that it needs is very, very low. Plus, being diamond, it's robust. It can work in any harsh environment condition. It can even work with the human blood, because diamond has a very low sticking coefficient for thrombosis to occur. So these are the one of the features. And then the most important thing that you would like to see is that if I make the gear out of diamond, how long it will last. So we actually created a small machine where we are actually causing it the friction to occur along this edge, and then we are looking at the wear with respect to number of cycles. So what we see is that previously there is some little wear which is actually happens during the polishing of these asperities. Once that is done, there is no wear at all. So even after millions of cycles, if you use silicon, within few hundred cycles the whole device is gone. But here, even with the millions of cycles, nothing happens through diamond. So this is one of the robustness that diamond micro machine can provide. So where it can be used, there are many applications for microsurgical tool like biopsy. It could be minimally invasive. It could be micro gripper in corrosive liquids, and that could be used to pick and place the objects in a MEMS switches. This is again for electronics, MEMS, just like the RF MEMS switches that I mentioned for communications, and also for causing different things to move in a different direction at different length scale by using the wear resistant micro gears. So for space application, also for moving the mirrors and everything that could be used. Now let's go to the different topic now, and I'll talk about some of the next generation STEM kit that we have developed in collaboration with the United Scientific. So can a single conductive diamond edge produce a wire? So here what we are doing is insulating wire and depositing a conducting diamond, and then again insulating layer, and then putting that into electrochemical cell like a copper sulfate, and then applying the voltage and seeing whether a copper wire can be deposited on a diamond conducting edge. And then what we see is that yes, very beautiful gold wire in this case is fabricated in a very simple way in this case. So that was really exciting to see that you can deposit a nice nanowires, not just copper or gold, many different wires, which you can have the ionic liquid or the electrochemical solution, and so you can manufacture different wires, different shape by using this process. Now the question is, why diamond? So first of all, diamond is chemically inert. So if you create a template with the diamond, then you can deposit and remove the things off the diamond and reuse that template again and again. So it's a kind of a mass production that you're utilizing, and the template is never sacrificed. So this is a breakthrough for the nano manufacturing technology for producing nanowires, which could be used for various applications. So these wafers, you can make any kind of patterns, even your school logo, whatever. And then once you deposit, you can reuse. So this is a scanning electron microscope image of that edge, and then you can make either nanowire or microwire, depending on whether you are depositing much longer. So we can make different nanowires of different materials, different shape and sizes. and then you can put a polymer on top. Even you can put a scotch tape and peel off, and send it to another area. In fact, one of the Octon Community College, some of the students have a project. They are working with us, where they are making a hand warmer. So they are actually, creating these copper wires, and then, transferring it into the fabrics, and they're going to attach, a 9-volt battery, and then, it will be like a hand warmer, because, you can manipulate the resistance that way. So, so this is a beautiful technology that once you have the template, you can make nanostructure without going into the expensive clean room. And that's a great way. Now we are working on, and for technological applications, it is in many different areas like RFID, security paper. You can have, make solar cell. In fact, that's the next generation now we are working on. So you can make a solar cell screen print, and then you can just apply, the light, and you will see the voltage generated. So within 5 minutes, you can make a solar cell in your lab, and that's a great way, to explain, the processes involved, and the student can make the solar cell by, themselves and test the properties. So it's a very nice way of, learning the nanotechnology and also learning about science. So, well, I mean, these are the different elements and metals that we can make out of just by using this 9-volt battery electrochemical cell. In fact, if you have the electrochemical solution available in chemistry, you can make all this thing, you can synthesize the whole library, on your lab, in your lab. So these are the different nanowires that we have fabricated. You can even make a flexible, nanowire network. In this case, it's a copper and nickel nanowire that we have made. And then if you look at the EDX, which actually look at the different elements, you can clearly see which one is nickel, which one is copper, and the fabrics that we have fabricated here. So this could be used for many different applications, even medical clothing, antibacterial, bandage and things like that. So this is now a product already available in the market, and I don't have to say much because you already have that here. And I think I'll be, Dr. Menon is setting a visit of few students from here to the CNM, where you will get to see not only that setup, but can utilize it and do some many experiments, as you can do here also. This is just one examples making this kind of nanowire. You can transfer it and make a pressure or a touch sensor. So what you have here is a glass plate, and on the glass plate you transfer many of those nanowires, and then these are the just two electrical wires coming and completing the circuit. So the gap that even you don't see anything in there, these are the nanowires. So if you touch that, it will complete the circuit, and then it will make the LED lit. So this is a very rudimentary way of making a touch sensor here. But you can, your imagination can go wild, and you can do many different things once you have this kind of tool available in your hand. So let me go on to the graphene a little bit. So as I mentioned, these are the two scientists from Manchester University in UK, and they discovered that in 2004 and 2010 they awarded Nobel Prize. This was the fastest Nobel Prize actually, after discovering in 2004 and then making it to the Nobel Prize because of the extraordinary properties that this material offer. Now, what is this exactly graphene? As I mentioned, if you take a graphite and if you can isolate the one atom thick layer, because graphite is formed by layer structure, so it's very easy to peel. In fact, when you're writing with your pencil, you are actually exfoliating that graphene, and that's why when you're writing it, that's actually multi-layer graphene. If you write something on a paper and put it under the electron microscope, you will see many layers, which is actually individual layer is a graphene. So there are many different applications coming up in flexible and wearable electronics, where you can measure the different electrocardiogram. Not only you can also measure your blood sugar and everything. So many things going on in electronics world, but I was mostly attracted by its mechanical properties. Just one atom thick, but there is a very nice cartoon which shows if you have a pin on top of this 1 atom thick graphene, it can balance a whole elephant, because its Young modulus is about 1 terapascal. So it's a very, very high. I mean, this is the highest Young modulus of any material that you can imagine. It can be stretched 20% more than its original size. And so we were wondering about, if the mechanical properties are so good, what about the wear friction properties, which is called as tribological properties. So we started working in this area from last 6 years, and then if you talk about friction, you will imagine where the friction is used. I mean, if you look at the various examples that I'm showing here, whether it is micro machines or wind turbine or even your car, your efficiency is always affected by the friction in those machines. So if you can reduce the friction even by a small amount, you are actually gaining a lot in terms of not only energy efficiency but the cost that is needed to produce. So just an example, if you take your internal combustion driven car and then look at the energy dissipated through different components when you are moving car, and if you look at the only energy that is dissipated or the go west by friction is about 17%. Okay, so 17% of your car is mostly affected by friction, and that's where the mileage, when you talk about mileage, is all about friction in your internal combustion engine, and that causing that kind of friction, the loss. So imagine if we can reduce that to near zero, then not only you will have a mileage which is very great, but you can also reduce the emission of hazardous material, because mostly these friction reducing agents are oil based, and they produces hazardous waste into the environment, because you have to dump the oil somewhere, or you have to burn it, and that always creates this kind of environmental hazards. So we are always working on how we can reduce that. If there's any way we can completely eliminate oil by using some next generation lubricants. So we started working on graphene, and then here some of the example. This could be a little bit technical for you, but if you just look at the advantages here, as compared to the oil-based lubricants, it requires very, very small amount. Just few drops can actually cause a lot of changes in your wear friction properties. You can apply much larger area, and then if you just compare, there's a steel surface. In ball bearing there is always steel rubbing against steel, and if you compare with the rest of the lubricants which are already out there, the wear is reduced by 10,000 times, and the friction is by 6 times, just by using this atomically thin lubricants that we have established. And the cost for doing that is also not drastic. So this is the next revolution that is coming up in lubrication industry right now. So just to give an example, if you look at the friction of a graphite, which is used as a lube, graphite lube as a lubricant, in most of the applications, it works only in one area. Like in dry nitrogen, when you are actually in a much drier environment, for example, in Chicago winter is very dry. So if you have a lube, graphite lube, and you might have actually experienced this in your lab door knobs. So they more squeak in winter because the lube in there is not working, and that's the example. So if you use graphite lubes, it has very high friction in a dry environment but low friction in humid air, but if you use the graphene, whether it is dry or humid, you have always low friction. So that was a first breakthrough that we achieved in the lab, and then we started working on it with the industry. So we came up with another process. Again, this is a little bit more complicated. So in this case, we actually combined the graphene with the nanodiamond particles, and that's where we reduce the friction to even in near 0.004. So even 10 times reduction in friction here. So now we are actually working with different industries, and some of the industries which are right here from Illinois. This is called dry gas seals. So I don't know if you have seen a movie called Event Horizon. where actually they are pumping the oil from offshore, and then there is explosion happens because of the leakage, and then the whole platform burned down. And that is a specifically very hazardous condition that these men work in a very adverse environment. So if the seal fail while you're excavating the gas or the oil, is because of the wear friction properties of that particular seal. So this is the biggest the loss that this company can endure if their seal doesn't work. So they are working with us now in reducing the wear and friction by applying this kind of coating to their seals. Now another examples is also this is another program that we are working with the company called Magna. So you might have seen that the car has a different shape and sizes. So what they do is they actually come up with a metal foil and they stamp it at a little high temperature, like 400 degrees Celsius, to have the shape of that car. So when they do it, there is a metal-metal contact, so there is a friction. So if we can reduce that friction, then you can again increase the energy efficiency of the car. And one of the processes that they use is, if currently they use oil-based or some hazardous solid lubricant, so they have to remove it and then paint the car. So if we can eliminate that steps with the graphene, that would be great. So this is another program that we are working. So hopefully within the next few years, we'll have another revolution in that industry. Now there are many other applications. I'm just listing few here. Wind turbines is another great examples. You need some minimum wind speed to turn the wheels of the wind turbine, and that is because of the inertia, and that is because of the friction. So if you reduce the friction to near zero, then even with the small wind speed, you can have energy production. So you can imagine after few years, you can install your personal wind turbine on your home, and that can power your home completely. So that's the kind of thing that we are working on. The another is in computing. So hard disk drive are still used in advanced computing, also for data storage at large scale. And in case of hard disk drive, there is a very thin lubricant on the hard disk drive. So when there is a power outage, the head snaps onto the your data magnetic disk, and that can scratch, and that cause the loss of data. The another important factor is the storage density of the disk drive can be increased if the distance between the flying head and the magnetic storage is smaller. So with the graphene, which is 1 atom thick, it also has anti-corrosion properties. Then it will not only increase the storage density of the hard disk drive, but also the lifetime. So that's the area that we are now concentrating on. So I just wanted to give you an perspective of what goes on into the research in big labs like Argonne National Labs. So we work on the basic research, which is if you look at the iceberg model, so you only see the tip of the iceberg, but you don't know what goes around, which is all basic research. So it's from the breakthrough idea to come to the conclusion, and then what you see is the technology development, and finally the product. That's what you see. But everything that goes around is all basic research. So just by thumb rule, any technology that starts with the idea to come up with the product takes about 10 to 15 years. So any idea that starts now, it's going to take 10 to 15 years to come up with the product. So all that time is spent in actually how we can take the idea into the product. Now, even in the technology development space, where most of the company work within this space, there are a lot of different sub tasks into this, and then that comes with a scale-up cost, yield, reproducibility, performance matrix, test trial, and then finally the product launch. So the company also has their own schedule. So it starts at National Lab, taking the technology, having patents licensed by company work around it, and then they come up with the product. And what you see, in the market is the final outcome of all this kind of investment. So it's a big cycle, that goes through it. So finally, as a student, I think for you, I really would like to take home with this message is your great ideas today, going to change the world for tomorrow. So what you do here today is very, very important. I mean, because you are the central focus of all the technological development that is going to happen tomorrow. So when you go into your lab, when you are doing your homework, you are doing most important things, and your passion is the one that's going to take from here to somewhere else. So what I'm saying is just think big, always dream big. That is the most important thing. Thank you.
Thank you, Ani. That was a wonderful presentation. I enjoyed it immensely. I hope you all did as well. If you have any questions, we have some time for questions. Anything you would like to ask Dr. Sumant? Now, maybe this, maybe Dr. Fields has a question,
Sure.
so I'm going to, there, he has a mic for you.
Talking to a microphone. My question is, you talked about the properties of graphene being one layer, and then you talk about coating the graphene on different components through a spray. And every picture looked like a hairspray bottle.
Yes.
Is that really how you're going to get one layer, or it does more than one one layer?
I think there are different. When I say about, I couldn't go into much details, but for electronic properties, that people are using it in electronic circuits and sensor, the one layer there is important. Whereas for tribological properties where we are working, you need more than one layer, few layers. And that's why we are coming up with a spray process. In fact, now we have another machine that can spray coat on much larger area, where you can pinpoint any area and then you can say that, yeah, there will be 3 layers, there will be 4 layers. So because the friction between the layers, the shearing between the graphene planes is very, very low, and that gives the low friction. So when I say about graphene for tribology, it's not one layer, it's more number of layers. Whereas for electronics, yeah, it's one layer that is more efficient. Yeah, then by using the CVD process, you can make on copper, grow on large area, just a single layer. Yeah. Any more questions from students? Come on, students, you have to. Yes. Yeah, that's a very important question. I think my interest in science, I knew that I had to do science when I was in 5th grade, and the credit goes to my teacher. So, and that teacher was not even from science, it was a language teacher. And one day the teacher came and said, we're not going to talk about anything today, we'll just talk about what you want to be. And he started asking questions, to each student what you want to be, and everyone was giving answers that movie star or doctor, engineer. And suddenly I said, I want to be scientist. And I also didn't know why I said that. But when I started thinking later on, is that every day when my dad used to come back from office, he used to take me to the library. And I used to read the books mostly which are scientist biography. And that somehow got implanted in my mind, and that answer came out through my mouth there. But with that question and answer session, that actually triggered my thinking, and that's how I went towards science. So that's why I think it's in your mind. You need some kind of trigger, and that's why if you're not sure, and you're not sure at that point, at that age, what you want to be, that's why you go to the great resources. And I think what the faculty is doing here is a good thing, that to exposure, give the exposure to different areas, not necessarily, of course, science. Some wants to be completely different area. So expose yourself while you are here to different field, then you will know in much greater depth that what you want to be.
Give me 1 second to pass it over.
I'm off guard. Did you throughout your whole career, right? Do you find it gets easier doing what you do, or do you think it just remains the same challenge?
Yeah, that's again very important question. In fact, I thought that my days in high school, that those were more difficult, than during the PhD, because in high school and things, you're looking at small things, and maybe I was actually, believe it or not, I didn't like mathematics at all when I was in high school. Even though when I actually went for physics, major, mathematics is the major thing, but somehow I was not intrigued by the mathematics. But when I went to as upper level, deep thinking about where it is used, then I could relate that, oh, this is where it is used. Differential equation was kind of problem for me, but when I saw where it is used, and then I got a kick out of it. So I think as you go, to my personal experience, go upper, you go more deeper, and that's more fun. It's what is important is keep your passion. Never, think that this is not interesting for me, because today it may not be interesting, but tomorrow when you go to another advanced class, and then you will realize why it was important to do that. So I think nothing is difficult in this world. Nothing. It's just you have to keep pushing, keep focused, and then you will find it very easy.
Do you find it like if you ever like go back and like kind of do like easier, like I guess like science, easier stuff that you used to do you find it more fun, or do you just kind of find it like it's too easy, like I just
No, I mean, I always looked at every problem, as a kind of, because I looked at that problem because I was keenly interested in it. I never thought about whether it is easy or whether it is difficult, but I found those very, very interesting. And you realize when you are working on that problem, nothing is easy, but if you are genuinely interested, you keep doing it, and you will find the ways around it. So it's not question of easy or difficult. It's just you have to like it. If you see your heart, your brain is around it, your mind is around it, then you will figure out the way around it.
Thank you.
So what are some future careers that this can lead to?
Yes, very important question. So, in case of scientific or technological areas, at Argonne, of course, there are many different areas that we work on, and you be a scientist, and one of the examples that I always give, and this is including my son, because he was always asking me that, okay, this is the nerdy area. What you don't make necessarily more money around it, but I said no, that's completely wrong. Because when you are a scientist, you are developing technologies. You are kind of an entrepreneur, and some of the examples that I mentioned, we were able to spin off many different companies. So a scientist is not a boring person who goes inside the lab and work around the clock. It's not like that any longer. You produce new technology. You work with the companies. Your patents is being licensed by these companies, and that's how it's a very rewarding career. Not just that you are interested by some and you are not a mad scientist. It's you look at Elon Musk, and how he started his career and things. So there are many different areas that you can work in this, and Argonne National Lab is a great resource. I'm talking about only my discipline, but as a biologist, as a chemical engineer, as a physicist, there are huge number of opportunities in this area. So if you consider science as your career pathway, I would also suggest you should also come to a career for women as an engineer at Argonne. Every year, there's a big festival at Argonne. There's a big career festival that. And this is for women, and also there is another for everybody, and it's a great way that you can learn about what are the career pathways in a science. So that just happened actually last month. So it happened every year around in this time. So you should just check the Argonne webpage, and you will easily find out.
Okay, we have one more question.
Yes, hi. I was just wondering, like the graphene currently, like where is it being produced? Is it just at the lab right now, or how widely throughout
Yeah.
the states or the world can it be produced?
Yeah, no, that's a very excellent question. I mean, the graphene, as I started, I said it's 2004, the first, the work started at Manchester. And after 2010, when the Nobel Prize was announced, everywhere in the world, there is a huge amount of research going on in the graphene. So there are companies right now producing graphene. In fact, we are helping some of the companies here in Illinois to produce graphene, and there are products coming out. I actually, hold one of the graphene conference every year, where they talk about what are the new products coming up. So last year it was in Tennessee, and then there was a showcase about a new water filter that is created with the graphene, and then it's a much more cheaper, efficient water filter. And then they actually also, there is a sportswear now they are coming up with all kinds of fancy products now. So the sportswear is when you wear it, and this is for like Olympic athletes, where even a fraction of a second matter, so they are using this sportswear that allow them to dissipate the heat more quickly, and they don't feel tired. And there was a bike that was also fabricated with a graphene enhanced composite, so the weight is very less and the mechanical stability is much higher, so the athlete can go at much higher speed. Now there are some high-end technology products that we are working on, including graphene as a lubricant, as well as sensors that can detect hazardous chemicals, like if there is any bomb that is someone carrying in the backpack, just by the vapors that come out of that, you can detect. Biosensors like anthrax and others, that's another area. We are also developing some of the sensor that can even detect some kind of a nuclear pollutant into the water. So if there is any nuclear waste going into the water stream, that you can detect that. One of the application that you will find it very interesting that we are working on is a tunnel digging sensor. So across the border, and this was a company that we were collaborating with in Israel, that they are working with tunnel digging sensor, because if someone is digging a tunnel across the border, the frequency is very different than the troops going or the tanks going around. So the graphene being as a very high frequency or high young modulus, even a tiny vibration can be detected. So if you analyze the data, you can actually differentiate between the man walking or the troops walking versus someone is digging a tunnel. So that is for enhance national security area and things like that. So there are tremendous applications now that are coming out of this graphene, and some real products which are already coming out.
What's the cost?
Yeah, that's again important question. Is the cost is always the major factor for producing anything. So when in 2010 that the prize was announced, the cost of graphene was very high, but now just within 7-8 years, the cost of the graphene is going even more than half. So now we can produce graphene, which was previously like $100 to $500 per gram to like a dollar per gram now. And the same for the CVD grown. So you can now produce CVD grown graphene on roll-to-roll basis. Previously we were growing it on few samples, but now you can grow on roll-to-roll basis. So very much large area graphene. So the cost is not a problem. I mean, if you see a lot of advantages in its properties, the people will work around the cost. And the source of, I think the only limitation there is where you get graphene. Graphite mines is the one. Same limitation is for lithium-ion batteries. So lithium is coming from mines, and so the natural resources are the main bottleneck there. But as long as for graphite, there are many natural resources that you can excavate graphite and then converts into graphene. But for CVD, you don't need that. For CVD, you just use methane gas and produce graphene.
The nanowire as well, like the cost to produce that?
Yeah, I mean, the main reason why we were interested in a nanowire project was because we were working on how to mass produce nanowires. Because conventionally, the nanowires are, deposited by using the chemical vapor deposition, and the yield is not that high. So we were thinking if there is any electrochemical method, that can be produced. But the existing electrochemical methods always use a template which needs to be sacrificed, only one time used. So that's how we came up with the idea of using diamond as a reusable template, and that completely, changed the game. Because you can use the same template over and over and can mass produce this, nanowires on large area. So that was the major breakthrough. But then we started thinking, because the collaborator with which I was working with, Professor Mike Zack, he was from a university, small university, and he was also thinking about, yeah, we discovered this, but how can we translate that for students' benefit? And that's how we came up with the next generation STEM kit. So you can have this kind of electrochemical set, which is driven by 9-volt battery in your classroom, and the student can learn about electrochemistry, learn about nanowire manufacturing, and can build some small circuits, and that's, I think, a great way to teach them. So.
On that note, I would like to, repeat that we do have Dr. Sumant's kit in Chem 132 for the honors students. We are going to do that, and I will open it up to the other students. I'll let you know when we do that experimentation. Maybe you can't participate in it yet, but you can at least observe it. So we do have that kit, and we'll utilize that. And I would like to thank Dr. Sumant now for his time. Unless there are any other questions that we have. If you get a chance to view his talk again, that would be a wonderful thing, because I don't think you will remember everything that he talked about. His talk, every slide had nuances in it. Depending upon what level of science and technology you are at, you could glean a lot of things. He talked a lot about applications. So even if you don't watch the video again, something that he talked about, maybe one thing that might have, that you might notice, please go about learning about that a little bit more. Go home and pick just one thing that he talked about today that interested you, that caught your attention. Maybe it was an application, maybe it was a phase diagram. I don't think so, but you never know, right? But we will talk about phase diagrams a little bit later if I haven't touched on that yet. But whatever it is, just pick one thing, because every time I see you, I can never leave you without giving you something to do, some homework or something, assign something for you to do, right? So I want to urge you to take up one thing that he talked about that interested you and find out about it. Find out more about it. And then when you come back to his presentation, you will find that he mentioned something more about it that you might not have gleaned at that first thought. Okay? But with that, I'd like to thank Annie. Thanks for being here. Our pleasure to have you. And let's give him one more round of applause.
Thank you. Thank you.